So, hi everyone. This is lecture 3 of AI and machine learning. Okay, for the Google Student Developer Club. Okay, so today we're gonna go over optimizers. So, what is an optimizer? In our machine learning algorithm, we're gonna have an objective function. We're gonna have a function that we want to optimize. Most likely, it's your loss function. So we want to minimize that. We want to minimize loss throughout training. So you might think to yourself, well, if we have a loss function, I remember from calculus how to find the minimums. I take the derivative, or if it's a vector function, I'll take the gradient, make them equal to 0, and then I'll get a bunch of max mins, and maybe I'll get a saddle point, and I don't want the saddle points, so I'll check the second derivative, make that equal to 0. Problem is we're dealing with an n-dimensional input, m-dimensional output, and sometimes, or nearly all the time, you can't do that analytically. You have to use an algorithm. This kind of ties into Euler's method, if you remember that from Cal 1, or if you did numerical methods. Sometimes a function's too difficult to integrate analytically. Same thing, it's too difficult to differentiate analytically, so we'll have to have another method for that. And Euler's method is a great way to start thinking about optimizers. So let's start off with gradient descent. So what is gradient descent? I'm going to draw what a loss function could look like. All right, so think of your objective function, okay, as a mountain. So it has a bunch of valleys and peaks. So if you remember from calculus 3, okay, it could look like this. Okay, these are our contour lines, and let's assume this is our objective function. We'll call this J of theta. Remember, theta is the parameter of our model. Okay, and we want to find this minimum. So in 3D, it will look like a amount or a value. Okay, and these are our contour lines. So we want to, and we assume we can't analytically do this. How are we going to do this with gradient descent? Well, pretend you're like skiing. You want to follow, if you want to ski as fast as possible, you want to follow the path that has the greatest rate of change, okay? The path that will increase your velocity the most. That's basically what gradient descent is doing. So we have gradient descent. Okay. Gradient descent that will take in, we'll have a few parameters. So we're going to do this in 1D so that, let me just see if the board is legible. That's okay. So we're going to do this in 1D so you guys can understand. But that again makes you think, oh, you could just do it analytically, but it's just so you could visualize. So we're given a function J. We want J prime. J prime will be turned into, well, when we do multi-dimensional, we're doing 1D, we'll make that the gradient. But for now, it's just the derivative. We're given theta initial. And we're given eta, Greek letter, and epsilon. So J is our objective function. J prime is our derivative. Theta initial is our initial theta, where we're going to choose to start on our objective function. And eta is going to be your step size, or rather learning rate. So think of when you're, let's say, walking down this valley, how big of a step are you taking to go towards that minimum? And epsilon is going to be thought of as a threshold that we'll be happy with when we reach that minimum. So how does this work? So we're going to say this is our gradient descent algorithm. Okay. So right here. So theta will equal theta. Sorry, I'll write this. It's variables. Theta will equal theta initial. And then we're going to loop through, we're going to say theta. We're going to loop through all our thetas, and theta is going to equal, or theta nu, I could say. Theta nu is going to equal theta old minus eta times f prime or j prime of theta. So what does this mean? All it means, I'm going to return well, we're going to loop, we're going to do this until theta, or f prime of theta. Yeah, f prime of theta is less than epsilon. Or j prime. And then we're going to return theta. So we're going to try to find that theta that we will reach a certain range where we're happy, and then we're going to return theta. So does this concept kind of make sense to you guys? Basically, how does it look? We're going to start here, and then we're going to take a step. We're going to take a step where this is going to be our step size in the direction of the gradient. Always remember, just gradient descent, you're taking a step in the direction of the gradient. And then I'm going to take another step. And then I'm going to take another step. I'm going to keep going with a constant step size until I reach my minimum. Okay. Now, your function is not going to be this nice. It's not going to be one nice value, but one nice minimum. You're going to have local minimum and global minimum. You're going to have saddle points. You're going to have a lot of things. Gradient descent will find you a minimum for some theta. It most likely will be the local minimum. Okay. So what happens now? What are the problems? If your step size now, think of it maybe as a in 2D with a parabola. Okay. All right. We're going to start here at theta initial. So this is j of theta, and then this is theta. Okay. We're going to start here at theta initial. I'm going to take a step in the direction of my derivative gradient. Here it's the gradient, here it's 2D, it's for 1D, it's derivative. Okay. I'm going to take another step till I reach my minimum, and then from here I'll go back and keep going back and forth until I reach that epsilon threshold. So what can happen? Well, if these steps are too small, it will take forever to reach the bottom. Okay. If I decide to go down the hill stepping as small as I can, I won't reach the bottom. Okay. If my steps are too big now, I may overshoot my minimum and then keep going. Now I'm here. I'm like, oh, I have to go back. I'll overshoot again. And I'll overshoot again. And I could go to infinity or nan. Okay. So you might, if your step size is too large, you overshoot your minimum or your optimum. And if it's too small, it'll take way too long to reach there. So gradient descent does not promise finding a global optimum. It is nearly guaranteed, however, to find a local optimum such that for any local optimum, there exists a step size such that you will have a theta within epsilon. All right. So what is, so just quickly, if you're wondering about epsilon, it's just f of theta minus f of theta minus 1. This is t minus 1 is less than epsilon. Okay. That's the magnitude of this. So that's what we want to do gradients until our interval is small enough, small as our epsilon. Okay. So 1 second. Now, how do we make this better? Because it's not that great right now. I mean, we'll find a local optimum, but it's not that great. So what we talked about is batch gradient descent. We're computing the gradients of the cost function or loss function, whatever you want to call it, using the entire data set. And due to this process, it's very slow, because if the data set is very large, all of your training data has to be stored in memory, and that's expensive. So we want to find a better way to do this. We could do something called stochastic gradient descent. So stochastic gradient descent is much more efficient than batch gradient descent for large models. So instead of using the entire data set to compute the gradients, stochastic gradient descent uses randomly chosen samples of the data set to compute the gradients, which is a lot better. Okay, we don't have to store everything in memory, and we're saving a lot. And already our model might be very intensive on VRAM, so this is a better optimization algorithm. So this algorithm updates a parameter for each training example one at a time, and it's a lot more efficient. So stochastic gradient descent is very similar. I'm just going to be choosing. So I'm going to say, again, theta is equal to theta initial. And then I'm going to choose a certain theta to compute my gradient instead of the entire data set. So let's say for t equals 1 to t, which is the size of my data set, I'm going to take an I, which is between 1 and n. And take some I, and then I'm going to say theta t is equal to theta t minus 1 minus our learning rate or our step size. And then it'll be the same as before. We're going to multiply by the gradient in terms of theta of our objective function. And then this will be theta t minus 1. Okay. And then we're going to return theta t. Okay. So it's the same thing, except I'm saving a lot on memory because I'm not computing the entire data set. I'm taking some data to compute the gradient, which is still good because if you think about it, we're averaging all thetas to compute the gradient. And this is just one portion of the average. So, or we might take a smaller portion, okay? Which will lead us into mini batch gradient descent, taking small portions of theta. All right, so mini batch gradient descent combines advantages of stochastic gradient descent and batch gradient descent, and it does this by performing updates on smaller batches of the data set. So this approach stabilizes your convergence towards your minimum by reducing the variance in your data. And it's also efficient on memory. All right, so although gradient descent as an algorithm is a great foundation for machine learning optimization, there are still many challenges and issues that arise in practice. Firstly, you have to know the right learning rate to use. We'll get into optimizers that have adaptive learning rates, so how big of a step we're taking. But sometimes just picking a learning rate on your own is very difficult to determine. It's a hyperparameter of your model. It'll depend on your data. It'll depend on your model, depend on a lot of things. Okay, if the learning rate is too large, as I mentioned, we overshoot. And if it's too small, we'll never get there. So that's why having a fixed learning rate is not optimal, because it may be too large, it may be too small. If you're lucky, it's good, but you want to have the correct learning rate. So it is possible to incorporate an adaptive learning rate, such as a learning rate that will be redefined when the change in the objective between, basically, you will change your learning rate as you're traversing your objective function. Okay. So we'll move into our next. It's still gradient descent, except it's incorporating a very, very, very cool thing called momentum. And you could think about it like physics. So to tackle the mentioned issue of gradient descent, there's a concept called momentum. Now, what is momentum? So if I have, what is momentum? Okay. If I'm going down this hill, okay, I say I'm stepping in a direction, I might have, you could think of it as if you're rolling a ball in this direction, it has a velocity. I'm going to take a portion of that velocity and I'm going to add that to my step to then make a better correction. Okay, what does that mean? So with regular gradient descent, we're doing a lot of these zigzags. Okay, so what is momentum do? Okay, I'm gonna redraw this picture vertically, so it might be easier to understand. Okay, so what is momentum doing? So I'm going to say I'm starting here. Then I'm going to take a step. Once I take a step, I'm going to compute. Yeah, I'm drawing this in another color now that I have these. Okay, I'm going to compute a velocity. Okay, a velocity which I will add in this direction, in the direction of the gradient. And then I will compute the gradient, the next step size. All this is doing is it's decreasing the amount of iterations or oscillations it will take to get to the local minimum. So in terms of complexity, you're decreasing, I believe, instead of it's by a factor of a square root, you're decreasing the amount of iterations that will take to get to your local minimum. So it's dampening these oscillations that your optimizer is doing. So how does it work? So stochastic gradient descent tends to struggle at locating minimums in areas that have very steep in certain dimensions. So it oscillates. And it may be, or definitely will be very inefficient in locating that minimum or optimum. Okay, so how does momentum fix this? It dampens the oscillations by adding or subtracting that velocity. So what does it look like? How much room do I have on the board? Okay, oh, right there. So what does it look like? Say V of t is equal to gamma Vt plus 1, where gamma is some parameter that you want to, it's how much of the previous velocity you want to keep, plus your step size, theta, j theta. Okay, so your gradient of your objective function. So that's v of t. Now what's theta? Theta is simply theta nu is equal to theta old minus v of t. So this is dampening my oscillations. So instead of reaching it in k oscillations, I believe it's root k. Okay, so it'll help a lot. So now this leads into another smart guy called Nesterov, which I believe is the student of the guy who made invented momentum. So here, what is Nesterov accelerated gradients? So it improves momentum similarly to how Euler's method is improved by improved Euler's method. If you're not familiar, Euler's method is a way to basically, if you're given function in terms of its derivative, could write the original function. Okay. What are we doing here? Basically, we're going to look ahead. What does that mean? So firstly, we're going to compute theta minus gamma v of t minus 1 in order to approximate the next position of theta. So I want to know where theta is going to be, and then I'm going to do my correction. So using this value, a closer approximation can be made of the gradient theta, okay? The Nesterov accelerated gradient algorithm can be expressed like this, okay? So v of t is equal to gamma v of t minus 1 plus theta. Can you guys see? It's good? Good. It's the gradient, what's the theta of j. Now instead of theta, it's theta minus this, gamma v of t minus 1. So we're looking ahead. I'll draw pictures so you guys can understand. Okay? And then theta is equal to theta minus v of t like before. Okay? So what does it look like? Okay. So what does classical momentum look like? And what does Nesterov accelerated gradients or Nesterov momentum look like? So if I have my gradient J of theta, okay. Oh no, this is just gonna be theta. Okay, if I have theta, and then this is going to be gamma v of t, and then this is going to be minus our step size times the gradient of theta. Okay, so this is regular momentum. We're computing this v of t, and we have our gradient, and then this is our new, this is theta nu. Okay, think of it as vector addition. Okay, this is where our regular gradient's going to point to. We have a correction, that little piece here that I drew earlier. Okay, that little piece of velocity, and how much we want to keep from the previous, how much we want to keep, and then we're summing them. Okay, what is Nesterov momentum doing? So this is momentum. What is Nesterov doing? Okay. Nesterov, we're starting with theta. Okay, this is going to be your gamma v of t. This is your velocity. Then I'm going to look ahead. This is going to be v of t plus 1. And then this is your eta g of eta is your, let me write that better. This is your other part. Gradient of j, and then we have theta minus gamma v of t. Okay. So, and then this is your new theta. Okay. So, what are we doing? Instead of computing our gradient and then adding our velocity, we're looking ahead with our velocity and then adding our gradient to get our new theta. So this makes the path we traverse more accurate. So Nesterov accelerated gradients makes large jumps in the direction of the previously accumulated gradients. The next step is then adjusted and corrected, which results in a more accurate assessment of the gradient compared to the momentum algorithm. Okay. The algorithm, yeah. So I drew it out for you guys. And then, yeah. Then there's, we'll have to talk about RMSProp before we talk about ADM. But to recap, this is the best you could do with gradient descent. So Nesterov momentum is the most efficient way to find local minimums with using gradient descent. Now, there are better optimizers. And often, like this is, if you use this for your models, this will be very good. Okay, if you use Nesterov accelerated gradients. But there is a newer optimizer that combines momentum and RMSProp. So RMSProp. Okay. As I mentioned before, our step size is our learning rate. Okay. If it's fixed, it's too big, we'll overshoot. If it's too small, we'll never get there. Okay. So what do we do, or how do we write an algorithm that has a adaptive learning rate? That comes into RMSProp, okay? Root mean squared propagation, okay? So I'm going to say our velocity term, v of t plus 1 is equal to, we'll keep gamma v of t. So the same as before, really, plus 1 minus gamma times our gradient squared. Okay, that's the change we're making. Now, what is theta nu? Is equal to theta minus our learning rate over epsilon plus our look ahead v of t plus 1 times our gradient. So what is this doing? We're changing now our learning rate depending on our velocity term. So if we have a greater velocity, we're going to have, if it's very, very big, we'll have a smaller learning rate. And if it's small, we'll have a greater learning rate, right? So that is RMSProp. Basically, we're changing our learning rate. It's the same as momentum, except now we have an adaptive learning rate. Okay, so as we're going down our optimum or our objective function, as we're trying to find the minimums, we're changing our step size. Okay, so just so you understand the analogy, gradient descent, to recap. Gradient descent, you're traveling in the direction of greatest increase. If you remember from Cal 3, the gradient is the partial derivatives of your vector function, and they will always point, your gradient will always point in the direction of max increase. If it's going down, it's negative. If it's going up, it's positive. So with gradient descent, we're always going to travel in that direction. Okay, until we get to an epsilon that we're happy with. Then we talked about stochastic gradient descent. It's the same thing. Instead of computing the gradients, the whole training set, we're just picking a batch, or for mini batch stochastic gradient descent, and for regular stochastic gradient descent, we're just picking a theta that will compute our gradient with, and then with that gradient, we'll do gradient descent. Okay. Then we talked about momentum. We have this velocity term that we will use to correct the number of iterations, the number of zigzags we'll do to get to our optimum. So it'll dampen. That's momentum. Nesterov accelerated gradients we're making our correction after we're adding our velocity term. So we first add that velocity term, then we'll compute the gradient instead of the other way around. Then now we're talking about RMSProp, same thing as momentum, except now we have an adaptive learning rate. Then the last and arguably best optimizer is adaptive moment estimation, which is short for ADAP. So when you're looking at these optimizers, you'll find a bunch of variations you'll find SGD, stochastic gradient descent, 1000%. That's what is used commonly and it's very good. But the best that you could get, and it may perform better than SGD, it might be overkill, but it may perform better for larger models, is ADAM, adaptive moment estimation. So it's an advanced optimization technique for SGD that deploys an adaptive learning rate for each parameter. Okay. So ADAM functions by storing exponentially decaying averages of past square gradients and non-squared gradients. So it'll store exponentially decaying squared gradients and regular gradients. Okay. And he'll do the average of all of that. These averages can be expressed by I'll write. I don't think I'll write it out. It's long. Actually, I'll write it out. Okay, write out Adam, but that'll be the last thing. There's one more that I wrote about a while ago, but it's very complicated. Okay, there's one more optimizer, but it's called. I'll mention it briefly after, but it's conceptual. Okay, so basically, what is Adam? So these averages of uncentered variance and mean of the gradients. So basically we're storing the averages of our square gradients and our regular gradients. And then a bias corrector is implemented to correct our velocity, and another term is called M of t. Okay, so combined, I'll try to keep the notation the same. Okay, so basically combining momentum and RMSProp will get you Adam. Okay, so we have a term called M of t, okay, which was what? Which was the averages of our gradients. The averages of our squared gradients will be expressed as v of t, I believe, yeah. Okay, so M of t is equal to here beta, we'll call it beta, and beta is the same as gamma. Okay, in this case, M of t minus 1 plus, I'll keep it the same. I wrote it that way, but I'll keep it the same. Okay, so we'll call it gamma, it's the same. Okay. Okay, so as you can see, it's pretty much the same thing as RMSProp, the first step for M of t, and then V of t is going to be, this was old momentum. V of t, which is here RMSProp, is going to be the same thing. Gamma V of t minus 1 plus gamma times, sorry. Sorry, this is the momentum component. This is your RMSProp component. Okay, as you can see, that was from earlier from momentum. Okay, now we have these bias correctors, I believe. Okay, so we're gonna say M of t hat is equal to M of t over 1 minus gamma 1t. Okay, and then your V of t hat is equal to V of t over 1 minus. Okay. Now the last, it just basically, it looks complicated. I'm writing a lot of things now, but all this is doing is it's combining. If you understand RMSProp, what are we doing with RMSProp? We're changing the learning rate and we're making it adaptive. We're saying our step size could change as we're finding our optimum, okay? Depending on where we're at. Momentum is we're decreasing the amount of oscillations we're doing with that velocity component. I'm computing these MFT and VFT, so I could write my last line, theta old is equal to theta old equal to, theta new is equal to theta old minus theta over epsilon plus root v of t plus 1 times m hat. Yeah, and this is v hat, m hat, of t. Okay. So there you go. So all we did with Adam is we combined RMSProp and we combined momentum. Okay. So this optimization algorithm is extremely efficient as it lowers computing costs, requires less memory, and is not affected by rescaling gradients. Okay, so basically, this is probably one of the best optimization algorithms you'll deal with. There are a bunch of variations of Adam, like Adam W, I believe, R Adam, which is rectified Adam, and then there's a bunch of variants. Okay, this is the most basic one, which just combines RMSProp and momentum. Lastly, there's other more recent algorithms. One I looked into not a long time ago was written about in 2021. It's called Ranger 21, and it's a very complex optimization algorithm that combines many optimizers. So what does that mean exactly? To make a better optimizer, I mean, these are very optimal, but to make a better optimizer, sometimes you'll find people combining many different optimizers. That is an approach you could go with. Okay, I won't go into Ranger 21. It's very, very complicated, but that is basically a very, very, very good overview of all the optimizers you'll deal with. When you're deploying your models, you'll probably want to use stochastic gradient descent with momentum, or you want to use Adam. A lot of defaulted models have Adam as their optimizer. Sometimes you could specify the optimizer you want. Okay, almost all the time. Okay, but if you're doing inference, just so you know, this is how Adam works under the hood. If you were ever training your own model, you saw Adam or SGD, now you know how it works. Okay. So what is a neuron? Okay, what is a neuron? So we'll have our neuron denoted by sigma. We'll have our input vector, and every input has an associated weight. So once our neuron will give a output, and the output will go into the activation function, and then we'll get the activation of the neuron. So for every input, there's an associated weight, and for every neuron has its own weight, W0, and then our input has weights W1 to Wn. A is the activation, or rather the output of the neuron. F is the activation function, and what is it? So your activation is equal to F of Z. Okay, Z is the output to our neuron, it goes into our activation function, we get our activation. Okay, it is the our activation Z is the sum is the sum from k equals 1 to m of x, yeah, k equals 1 to m of x I w I plus w naught. Okay. All right. So we want to pick w's so that our activation function does what we want, depending on our loss function. And this whole diagram represents one neuron. Just want to see if I missed anything. Okay, yeah. Last thing. Okay, this sum, this whole thing is equal to f of w transpose times x plus w naught. If you remember from, do you guys remember from lecture 2 what this is? This is our classifier. Okay, so our input to our activation function is our hypothesis, or rather our classifier. So what is an activation function? Next lecture, we're going to go over types of activation functions. But what is an activation function? So most basic activation function is f of x is x. We're going to, often it's nonlinear. Okay, often you have these nonlinear gates, as you might call them. That'll be your activation function. So the output of your neuron goes into your activation function, which will then output your activation A. Often it's nonlinear. We'll do activation functions next time, but yeah, that's pretty much what one neuron is. Okay, the input to our neurons are hypothesis or a classifier, and yeah, that's it. Okay, so let's talk about layers now. So we'll talk about fully connected layers. So fully connected layers. So W will represent a m by n weight matrix. So this is all our weights. W naught, which is the weight of one neuron, is going to be a n by 1 vector. And our input is x, which is n by 1. And then our output is going to be, let's say y, is going to be m by 1. Yeah. So our activation f is going to be, yeah, this is, this is y. Our activation is going to be n by 1. And f, so you saw f earlier. So f is going to take in our input z. Yeah, sorry, not y, z. F is going to take our input z as an input. It was f of z. You remember from the photo? Okay, z1 all the way to zn. Okay, we're going to, sorry, zn. Keep this as y. I'm getting confused. Okay, sorry. F is going to take in our input z, and it's going to apply. If you remember from linear algebra, how can a function take a vector as an input? That's weird. Okay, how do we do that? We're going to apply f element wise. So for every, you think of z as a, let's say, a column vector, and I have z1, z2, dot, 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 zn. Okay, f of z is going to equal f of z1, f of z2, dot, 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 f of zn, okay? So that's how we're applying f. Our activation function, it's applied, yeah, it's applied column-wise. Okay. So, lastly, what is a layer? A layer is simply a bunch of neurons stacked on top of each other, okay? But pretty much, you already know all the notation from the previous lectures. Now, we're just talking about it in a different way, okay? So next lecture, today was really optimizers. Next lecture, we're gonna go over convolutional neural networks. We're gonna go over activation functions, and then once we start, the beginning of the ResNet lecture will be when we start image classification. Okay, because we'll talk about the problem with convolutional neural networks, why, which is them scaling. Is adding more layers better? The answer is no. Okay. We'll get into, and then that leads into the paper of ResNet. Okay. And I'll show you the paper and we'll go through it. Okay, but that's it for today. So any questions? No? Okay. All right. Stop recording.